Students, welcome to Sunil's tutorial. I'm Sunil Nirvani and today we'll be doing this chapter called as stationary waves. Let's start. Now, last lecture we had seen how you would have stationary waves produced if the tube is closed at one end. Now let us consider that the tube is open at both ends. Tube open at both ends. Right? Now, if the tube is open at both ends, you would have waves that would be formed. In this way, right, where this is my length of the tube, you have half a wave formed here, so that means this is going to be lambda by 2, this length is going to be lambda by 2, this is my node, this is an antinode here and an antinode here. Fine. So if a wave is sent, the wave sent along a open tube at both ends, a tube open at both ends, the both ends are reflected at the other end. Reflected at the other end. Now the thing is, the incident and the reflected wave would interfere with each other. As the wave moves in, it will interfere with the waves that are there inside, that is the waves that you are sending in, right? They would interfere with each other and would produce stationary waves. The incident and the reflected wave, the incident and reflected wave would interfere to produce stationary waves. So even if the tube is open at both ends, as you send a wave, as you flow into the tube, as you send a wave in the tube, the wave gets reflected. The incident and the reflected wave would interfere with each other and would give rise to stationary waves. Finally, we get this in here. Now, at the open end of the pipe, the only difference being at the open end of the pipe, the air is free to move inward and outward. The air is free to move inwards and outwards with maximum possible freedom. So you would have an antinode produced there, possible freedom. Hence, antinodes are produced at both the ends. Hence, antinodes are produced at both the ends. Your maximum at both the open ends, you would have maximum space for the air to move, and therefore you would have antinodes produced at both ends. Thus, an air column in a pipe open at both the ends can vibrate in different modes. Thus, an air column in a pipe open at both ends can vibrate in different modes. Now let's see what are the modes in which it can vibrate. Now the simplest way of vibration would be called as can vibrate in different modes with the boundary condition that there must be antinodes at both ends. The boundary conditions that there must be antinode at both ends. Since both ends are free, air would have maximum space to move, and therefore there would be antinodes at both ends. So if you have antinodes at both ends, then you can have the air column in a pipe that can vibrate in different modes. Now, the simplest way of vibration is called as the fundamental mode. The simplest way of vibration is the fundamental mode. What is the fundamental mode? In which two antinodes are formed at the two open ends, at which two antinodes are formed at the two open ends, and a node and one node at the center of the tube. So you would have a node at the center of the tube and you would have antinodes at the two ends, right? Now let's assume that if lambda is the wavelength and L is the length of the tube, lambda is wavelength and L is the length of the tube. In which case I can say from the figure, we have seen the figure, I can say that the entire length is divided into half lambda, right? That is, how do I know it is half lambda? Half lambda is because it is the distance between two consecutive antinodes, right? Therefore I can say that lambda is equal to 2L, right? Now let's assume that if v is the velocity of the waves, if v is velocity of the waves, if v is the velocity of the waves, then I can say that the frequency can be given by, and n is frequency of the waves, then I can say that frequency is velocity upon wavelength. Velocity upon wavelength. Wavelength is nothing but 2L. So this frequency is called as my fundamental frequency or the first harmonic, where I can say that n is fundamental frequency or first harmonic. Fine, do we get this here? This is the lowest frequency with which the air column in an open tube at both the ends can resonate. This is the lowest frequency with which an air column open at both ends can resonate. Fine, do we get this in here? Now, let's see if there are different modes of vibration. Let us try to find out another mode of vibration. Air column open at both ends. Right, so let's assume that you have a node, antinode, node, and antinode. So, So you have a node, antinode, node, antinode and antinode, right? Now in that case, let's assume that this is the length of the tube. Now the distance between two consecutive antinodes is half the wavelength. So this is half the wavelength, this is another half wavelength. That means you have total wavelength here. In this particular mode, you would have total wavelength. I can say that the next possible mode of vibration is where you have three antinodes and two nodes. The next possible mode of vibration. The next possible mode of vibration is one in which there are three antinodes, and two nodes. Right? Now, in that case, let's assume that n1 and lambda 1 are the frequency and the wavelength. Let n1 and lambda 1 be frequency and wavelength. Right? So in which case I can therefore say that lambda 1 is equal to the length. Right? Once I know that lambda 1 is equal to length, I can say therefore n1 is equal to v upon lambda 1. So that will be nothing but v upon L. Now I could multiply by 2, I could divide by 2. So I can say that this is nothing but 2 into v upon 2L. I'm multiplying by 2, I'm dividing by 2. But v upon 2L is nothing but the fundamental frequency. So in this mode, I have the frequency that will be produced will be twice the fundamental frequency. Right? Do we get this thing clear? So I can say that N1 is the first overtone.
So it's supposed to be 2N.
2N. Yeah. Right? So I can say that where N1 is the first overtone, which is equal to the second harmonic. Fine, do we get this thing here? Now, I can similarly work with another kind of mode. Let's have a tube in which node, antinode, node, antinode, antinode. Right? This is my node, antinode, node, antinode, node, antinode. Right? Now, guys, antinode to antinode is half the wavelength. So this is half plus half plus half. That means I'm going to have 1.5 wavelength. That means this is going to be 3 lambda 2 by 2. The entire length of the tube is divided. This is my entire length of the tube. The entire length of the tube is divided into 3 lambda 2 by 2. Right? I can say that the next possible mode of vibration, the next possible mode of vibration, the next possible mode of vibration is the one in which there are 5 antinodes and 3 nodes. Is the one in which there are 5 antinodes and 3 nodes. let us assume that let n2 and lambda 2 be the frequency and wavelength. If n2 and lambda 2 are the frequency and wavelength, then in that case I can say that the entire length of the tube is divided into 3 lambda 2 by 2. Therefore I can say that lambda 2 is 2L by 3. Once you have this, then I can say that frequency is nothing but V upon lambda V as it is by lambda 2L by 3. This is 3 times V by 2L. Therefore I can say N2 is 3 times N. So that V by 2L is my fundamental frequency. So therefore this is my second overtone and this will be equal to the third harmonic. This is second overtone or third harmonic. Right? That means I can, yeah.
There are four antennas. You've written
1, 2, 1, 2, 3, 4. There are 4 antinodes and 3 nodes, right? Right? Now this is going to be my second overtone or this is going to be my third harmonic. Thus, the fundamental frequency along with its harmonic is produced by the tube which is open at both ends. I had the fundamental frequency, then I had the second harmonic, then I had the third harmonic. That means I can say that the frequencies that will be present in a tube that is open at both ends will be N, 2N, 3N, 4N. That means all the frequencies are going to be present in this. Like in the case of a tube that was closed at one end, only the odd frequencies were produced. Here all the frequencies will be present. Fine. I can say thus the fundamental frequency along with its harmonics are produced in a tube open at both ends. Right? I can say that frequencies present are N, 2N, 3N and so on. Right? The frequency of the first overtone is 2N. Similarly, I can say that the frequency of second overtone is 3N. Thus, I could say that in general, the frequency of the kth overtone, is going to be equal to n times k plus 1, where n is equal to 1, 2, 3 and up to infinity. So that's how you would have frequencies produced in a tube that is open at both the ends. Next, let's see the next thing. What is a resonance tube? Right? Now, a resonance tube consists of a long, narrow tube whose one end is dipped in a liquid and the other end is kept free. Right? You would have prongs that would hit one end of this, a wave would be produced when prong would hit the open end. The wave would hit the water surface and come up. Since there is no free movement at the other end, there will be a node that would be formed on the surface of the water, whereas there would be an antinode that would be formed at the open end. Right? Now, this is going to be my length of the tube. Right? That is above the surface of the water, and you will have only 1/4 of the wave that is going to be present here. So this is going to be nothing but lambda by 4. Right? The length of the tube would hold only a wavelength, because I don't even have two antinodes. The distance between two antinodes would be half. Here you have a node and an antinode. That means only 1/4 of the wave would be produced here. Right? Let's write this down. What is a resonance tube? So I can say a resonance tube. Resonance tube is a long uniform tube. Is a long uniform tube which is open at both ends. Open at both ends. Right? I can say that the tube is placed vertically with its lower end inserted into the water. The tube is placed vertically with its lower end inserted in water. Right? A part of the tube above the surface of the water contains air column. Part of the tube above the water surface contains air column. So you would have air column in that particular part, right? The length of this air column can be changed by raising or lowering the tube in the water. That's the reason why we need the resonance tube. You can change the length of the resonance tube at your will by just dipping it more in water or removing it from water. So I can say that the length of the air column can be changed. The length of air column can be changed. The length of air column can be changed by raising or lowering the tube in water. Right? Now, with this arrangement, we have air column. We have an air column in the tube which is closed at one end by the surface of the water, whose length can be varied. Right? With this arrangement, what's the advantage of this arrangement? This particular arrangement gives me an air column in a tube which is closed at one end. With this arrangement, we have air column in a tube which is closed at one end and whose length can be varied. That's my advantage of resonance tube. Now, how do I use the resonance tube? A tuning fork is excited and held near the open end of the tube. tuning fork is excited and is held near the end of the tube. So you would have sound waves that would travel along the air column. These waves would get reflected from the surface of the water. Now, the sound waves traveling inside and the sound waves that are reflected from the water surface would interfere with each other. That would give rise to stationary waves. So thus, stationary waves are produced in a resonance tube, right? So a tuning fork is excited and held near the open end of the tube. Sound waves would travel. Sound waves would travel along the air column. Sound waves would travel along the air column. These waves are reflected from the surface. These waves are reflected from the surface. These waves are reflected from the surface of water. The incident and the reflected waves would interfere. The incident and the reflected waves would interfere, and to set up stationary waves, in the air column. Thus, we see that stationary waves are set up in the air column. Now, let's see how do we find out the frequency of the stationary waves that are set up in the air column. Let's assume that initially the tube is inserted in the water to such a length that the air column is extremely small. By holding the tuning fork at the open end, the length of the resonance tube is gradually changed. I go on increasing the length of the resonance tube. At a certain point of time, the natural frequency of vibration would become exactly equal to the frequency of the tuning fork, and hence the air column would resonate with maximum amplitude, emitting a very loud sound. So at resonance, according to the boundary condition, the node, if it is closed at one end, boundary condition says that the node would be formed at the closed end of the air column, and you would have an antinode that would be formed at the open end, right? Let's just do the experimental here. So I can say initially the tube is inserted. The tube is inserted in water to such that the length of the air column is very small. Such that the length of the air column is very small. Initially we keep the length of the air column very small. Now by holding a vibrating tuning fork at the open end, holding a vibrating tuning fork on the open end, the resonance tube is gradually raised. The resonance tube is gradually raised. Right? Now, at some stage, the natural frequency of vibration in the air column, the natural frequency of vibrations in the air column would become equal to the frequency of will become exactly equal to the frequency of the tuning fork. Right? Now, as a result of this, what would happen is that hence the air column would resonate and vibrate with maximum amplitude. Hence, the air column would resonate and vibrate with maximum amplitude. The air column would resonate and vibrate with maximum amplitude, emitting a loud sound. Right? Now, at resonance, according to boundary conditions, at resonance, according to boundary conditions, I can say that the node should be formed at the close end and antinode should be formed at the open end. A node is formed at the close end of the air column. A node is formed at the closed end of the air column, and an antinode node is formed at the closed end of the air column and an antinode at the open end. Right? Now, the length of the tube above the water surface is going to be the length of the air column. The length of the tube above the water surface is the length of the air column. Right? Now let us assume that this length is L, which is say L. Now we already said that since by boundary condition there would be only one node and one antinode formed, I can say if lambda is the wavelength, if lambda is the wavelength of the waves, that means I can say at resonance length will be equal to lambda by 4, right? Therefore I can say lambda will be equal to 4L, right? I can also say that at resonance the natural frequency is equal to the frequency of the tuning fork. At resonance I can say that the natural frequency of the air column, the natural frequency of the air column at resonance, the natural frequency of the air column is equal to the frequency of the tuning fork. Frequency of the tuning fork. Hence, I can say that V, let's assume that V is the velocity of sound in air. V is velocity of sound in air. If V is the velocity of sound in air, I can say V is equal to N lambda, but lambda we found out is 4L, so I can say that V is 4NL, right? So using this equation we can find out the frequency of the tuning fork. Fine. So do we understand how a resonance tube works, right? Next, let's see what are the chances of error in a resonance tube, right? One of them is called as end correction. What do we understand by end correction? Now, in this particular, when we were working with resonance tube, we had assumed that you would have a node that would be formed at the close end and an antinode that would be formed at the open end. Now it is not necessary that the antinode would be formed exactly at the open end. It would be formed slightly above because the waves would travel. See, if I had a tube like this is the close end of the tube. You would have a node that would be formed here. A node would be formed at the close end, and you would have an antinode that would be formed at a point that will be slightly above the open end. The antinode would be formed because there would be more space for air to move slightly above the open end. So therefore the antinode, instead of being formed exactly at the open end, would be formed at a distance slightly above the open end. Let's assume that this is my length of the tube. You would have some distance, say, let's assume that there would be some distance E above the open end where the antinode would be formed. Fine, do we get this thing clear? Now, I can say that in the resonance tube it is assumed that the antinode is formed at the open end. In resonance tube, it is assumed that the antinode is formed at the open end. The antinode is formed at the open end of the resonance tube. You are assuming that the antinode would be formed at the open end of the tube, but in reality the antinode is formed little beyond the open end. But in reality the antinode is formed beyond, the antinode is formed a little beyond the open end, right? As a result of which the air molecules have maximum freedom to vibrate just outside the open end and not at the open end. The air molecules have maximum freedom to vibrate. The air molecules have maximum freedom to vibrate just outside the open end. Outside the open end and not at the open end. Right? This would give rise, therefore the length at which you would have resonance taking place would change. So I can say that the distance of the point where the antinode is actually formed from the open end of the tube is called as the end correction. That means the distance where the point where actually the antinode is formed and the open end of the tube would be called as your end correction. The distance of the point where the antinode is actually formed, antinode is actually formed from the open end of the tube, open end of the tube is called as end correction. This is my open end of the tube. The antinode is formed at this point. This distance between the open end of the tube and the point where the antinode is formed would be called as end correction, right? Let us denote, let it be denoted by E. Let it be denoted by E. Let's assume E is the value of the end correction, right? Now, the value of E will depend upon the diameter of the tube. The value of E would depend on the diameter of the tube. Right? Now, it has been found out according to a scientist, according to the scientist Ray Legin, E is about 0.3 D. The value of end correction is 0.3 times D, where D is the internal diameter of the resonance tube. Where D is the internal diameter of the resonance tube. Thus, I can now say that the length is not going to be equal to L, but the length is going to be equal to M plus 0.3 D will be equal to lambda by 4. You have one node, one antinode formed at a distance of L plus 0.3 D, but I can therefore say that lambda is equal to 4 times L plus 0.3 D, right? So using this equation I could find out, using this equation, and the velocity of sound in air can be determined. If the velocity of sound in air is known, then the frequency of the tuning fork can also be determined. Fine, do we get this thing clear? Okay, we will stop this here for the day. Thank you very much.